observation means that every time we see something in the form 1 over x plus a dx, then we don't have to, we can totally skip the u substitution, and we know that our antiderivative is natural log of the x plus a. Okay, so that's going to be helpful in this section. So 6.3, partial fractions. So recall from college algebra that a rational function is a function that looks like r of x is equal to p of x over q of x, where p of x and q of x are polynomials. All right, so what I'm saying here is, I'm reminding you what a rational function is because section 6.3 is going to be all about solving integrals that involve rational functions. Okay? So some examples of some rational functions, and I'm going to give you 4 examples. So my first one I'll call r1 of x. So here's an example of a rational function, 5 over 1 plus 4x. Even though it's just a number, technically a number can be a polynomial, and the denominator is also a polynomial. Our second example of a rational function is 1 over x squared plus 9. My third one is a little more complicated. X cubed plus 3x squared plus 4x plus 1 divided by x squared plus 3x plus 2. Okay. Another example, slightly more complicated example of a rational function. It's still polynomial divided by polynomial. And our last one, our fourth example, r4 of x, is x over x squared plus 9. Okay. So here are 4 examples of rational functions. Now, the really, really cool thing about rational functions is that every single rational function can be integrated. Okay? We can manipulate these guys in a bunch of different ways. We can break them down so that 100% of rational functions are something that we can integrate. So, cool property of rational functions is that every rational function can be rewritten so that we may find its antiderivative. All right, so if I go back over to these examples, maybe I look at the very first one. In the first one, if I want to calculate the integral of 5 over 1 plus 4x dx, I'd look at this one and I might say, okay, what am I going to do with this? I could look at a u sub for this one. And so I might look at a u sub where u is equal to my denominator. U is equal to 1 plus 4x. And then I could work through the calculus and the algebra on that and eventually come up with some natural log.
Hold the 5 on the top and pull it to the outside, and can we just use the observation we used earlier?
That's a really good observation. I can bring up 5 to the front. I do need to be a little bit careful because the reason that this one works is because my dx and my du are equal to each other, whereas here my dx is going to be equal to du over 4 because I'm going to have that 4 in front of the x. So I actually probably would want to write that out a few times to see what's happening with that. Good. Right. If I did not have the 4, then we could just use that observation we have over there. Okay. So we can do a u sub on that example. On our second one, the integral of 1 over x squared plus 9 dx. when I look at this one, this looks really similar to this looks like the form of our arctangent. So this is of our form, the integral of 1 over a squared plus x squared dx. And so then you could work with that, and so we would have, remember that our antiderivative is 1 over a times the arctangent of x over a. And so your a in this case is 3, and so you could work with that one. So this particular form, we know how to work with that rational function. The third one I'm going to skip, and then the fourth one. If I look at the fourth one down here, and I think about looking at the antiderivative of x over x squared plus 9. X over x squared plus 9. This looks very similar to the 1 over x squared plus 9, but very different. Okay, the 1 over x squared plus 9, that's of our arctangent form that we want to look for. But when I have x over x squared plus 9, here, when I look at my denominator and I think, okay, maybe I do a u sub, and I allow u to be equal to x squared plus 9. A u sub is a good choice here because our derivative is going to cancel that x on the top. And so this one we would work with a u substitution. Okay, so I encourage you to double check those three and work through them and see if you make sure that things work out well for you with those techniques. Becky?
Could you pull the x out of the top and then do the arctangent?
So pull the x out here. So I'm not allowed to do that because I can only pull constants out. And since x is one of our variables, it has to stay within the interval. Okay, other questions? Okay, so this other one up here, this Wigdinger number 3. So let's look at that one a little bit closer. The integral of x cubed plus 3x squared plus 4x plus 1 divided by x squared plus 3x plus 2 dx. All right, now when I look at this, a few things to think about. One is maybe I could try and split things up, but I've got a lot of pluses in the denominator, so that's not really going to clean things up for me. I might try a u substitution, but in terms of the u, I would want to choose the denominator, and its derivative is not going to cancel my numerator, nor vice versa. So u substitution also is not going to work.
Can you use synthetic division to reduce the coefficients? Translate it.
Okay, so this is a good idea. This idea of, okay, can we work with this fraction and manipulate it in one way or another? And the answer to that is yes. Okay? All right, so what's going to happen here? I'm going to write something down. It turns out that this integrand, this rational function here, can be rewritten as x plus 3 over x plus 2 minus 1 over x plus 1. All right, so you're saying, where the heck did that possibly come from? And we're going to figure that out, but for now, I'm going to put a little asterisk here and let you convince yourself that if you take these three fractions and you find common denominators and combine them together, that you will get back this big fraction over here. So I encourage you to check that out and see if that works. So this three fractions over here, if you combine them, you'll get back the original. The big question is, how the heck do you go from this big one and break it down into these smaller ones? And so, again, I'll put this asterisk here. We're going to answer that question by the end of the hour. But for now, let's just kind of skip that step. Just pretend, hey, oh, look, here's this fraction. This is another way of writing that exact same fraction. Once I have this fraction written in this way with these three separate fractions, or, well, with the x and the two separate fractions, once I have this is not too terrible to integrate. Look, I can can separate. I can look at the integral of x dx plus the integral of 3 over x plus 2 dx minus the integral of 1 over x plus 1 dx. And my first integral now is easy to deal with. That's 1/2 x squared. My second one, Ben's suggestion earlier is right on. We can pull that 3 into the front, and then we have 1 over x plus 2, and so we have 3 times the natural log of the absolute value of x plus 2 minus the natural log of the absolute value of x plus 1. And so if I just sort of pretend like somebody came along and said, oh look, this fraction can be rewritten, once that fraction is rewritten, then the calculus is not too bad. Are there any questions on the calculus part? Okay, so now the question is these asterisks right here, okay? How do we rewrite these complicated rational functions? And what I'm going to do is I'm going to give you a list of steps that we're going to follow. And this method that we're going to use, this method of rewriting a rational function like this one, the x cubed plus 3x squared plus 4x plus 1 over x squared plus 3x plus 2, rewriting that as something like x plus 3 over x plus 2 minus 1 over x plus 1. This method of rewriting these rational functions is called the method of partial fractions. All right, so here's how this method of partial fractions works. Okay? Again, this is a technique. Technically, everything that I'm going to talk about in this hour is really not about calculus. Because the calculus part we can do. It's the algebra that's the partial fractions, to go from complicated rational function to sum of easier fractions. Okay? And that's really what we're going to be talking about for the rest of the hour. Okay, so here's our method. Given a rational function, r of x is equal to p of x over q of x, such as our example. In our example, we're going to use r of x is equal to this complicated guy up here, x cubed plus 3x squared plus 4x plus 1 over x squared plus 3x plus 2. So given a fraction like that, our goal is to rewrite it. Now, a definition that we need is the definition of improper. Okay. A rational function is improper when the degree of the numerator is greater than or equal to the degree of the denominator. All right, so this particular rational function is improper. The degree of the numerator is 3, the degree of the denominator is 2. So top heavy. All right, so step number 1. If necessary, make our rational function proper. All right, now Mark alluded to this a little bit earlier. Can we do some sort of a synthetic division? Well, rather than thinking about, well, so if you prefer synthetic division, please go with it. I'm going to introduce this using long division. So in your college algebra class, or at some point in your life, you may or may not have talked about polynomial long division. So if this is the first time you're seeing it, please pay close attention. If this is the first time you're seeing it in several years, find that file in your brain. Okay, so here we go. We're going to make our polynomial, or our rational function, proper. And in order to do that, that means we need to use long division. So here's how this works. I'm taking my top, the x cubed plus 3x squared plus 4x plus 1, divided by the bottom. So I write this out using long division notation. I've got the x cubed plus 3x squared plus 4x plus 1, and we are dividing that by x squared plus 3x plus 2. Now, some things that I've glossed over here but are important is to make sure that your polynomial is written from highest power down to lowest power. If you are missing any terms, for example, maybe there wasn't a squared term in here, I might use a filler and say 0x squared if that were not here. So these are things to think about, but in this case, this is set up nicely already. So x cubed plus 3x squared plus 4x plus 1 divided by x squared plus 3x plus 2. Okay, so I'm looking at this long division, and I'm looking at my biggest terms, and I ask myself, what do I need to multiply x squared by to get x cubed? I have to multiply by x. And so I take that x, and I multiply it by every term out here in my divisor times quotient. So by my divisor. Okay. So we've got x cubed plus 3x squared plus 2x, and I'm going to subtract that entire polynomial off. Now, I need to be a little bit careful here, and you can certainly do this mentally, but I'm going to write this up on the board. I'm going to distribute this negative sign, so I'm going to change all of my pluses to minuses and all my minuses to plus. And so when I do that, the x cubes cancel. 3x squared minus 3x squared leaves me with nothing. And then 4x minus 2x leaves me with 2x. And then I still have 1 minus 0, which is 1. Okay, so what I've done here is I now have an x up on the top. This is my whole part. And then I have this remainder down here. I know to stop because my power on my remainder is less than the power on my divisor. Okay, so I've got my whole piece up here, and my remainder of 2x plus 1, which means that now I can write x cubed plus 3x squared plus 4x plus 1 over x squared plus 3x plus 2 as its whole part, which is the x, plus the remainder, which is still divided by the x squared plus 3x plus 2. So I have x plus 2x plus 1 over x squared plus 3x plus 2. Okay. So we are now done with step 1. We've taken our improper fraction, and we've written it as a whole part plus a remaining proper fraction. Any questions about this part? Okay. So the remainder of what we want to look at is we now want to focus just on the proper part of the fraction. The x part's perfectly fine. So step 2, looking at the proper part of our fraction, we want to factor the denominator. So factor the denominator into a product of linear and or irreducible quadratics. Okay, so we are so I want to focus on the 2x plus 1 over x squared plus 3x plus 2. And we want to factor our denominator. So take a look at that denominator and see if it factors well for you, and then write down your factoring. And then check with your neighbor and see if you agree on your factoring. Anybody agree? Your neighbor?
Yep.
Okay. All right. Anybody want to share with that?
X plus 2 and x plus 1.
Okay, x plus 2 and x plus 1. Anybody have a second on that one? Second? Good.
Third.
All right, and a third. Great. So at least 3 people agree. Okay, so we factored. So that's step 2. All right, step number 3. Step number 3 is to write the proper fraction. That's the proper part of what we're looking at. Again, this x we've already taken care of. We're still focusing on this proper part and breaking it down. So write the proper fraction as a sum of partial fractions with undetermined coefficients in the numerator. All right, so what the heck do I mean by that? All right, so I am taking this 2x plus 1 divided by x plus 2 times x plus 1, and I'm going to write this as a sum of fractions where I'm splitting up this denominator. So my first fraction is going to have an x plus 2 as my denominator, and my second fraction will have an x plus 1 as my denominator. Now, this part over here, write the proper fraction as a sum of partial fractions. Okay, I've got a sum. And they're what I'm considering partial fractions because they are parts of the denominator of my whole fraction. Sum of partial fractions with undetermined coefficients in the numerator. I do not know what these numbers on the top are going to be, so I'm going to call them A and B. Now, I'm going to put an asterisk on this particular step because the way to set this particular step up depends on what your factors are over here. We'll look at some other examples where our factors look a little bit different, then our setup will be slightly different. Okay? But for now, in this particular one where our factors are unique, they're different, and they're both linear, this is how we want to set this up. Okay. All right, so that is step number 3, and step number 4 is that we want to find what A and B are equal to. So find our coefficients. Okay, so this one is the shortest direction, but here's where the work comes in. Okay? So in order to find these coefficients, here's how this is going to work. On my left side, I have 2x plus 1 over x plus 2 times x plus 1. On this right side over here, what I'd like to do is to combine these two fractions. So in order to do that, they've got to have a common denominator. In particular, they're eventually going to have the same denominator as what I have on the left. And so this first one, I'm going to have to multiply the top and the bottom by x plus 1. And in the second fraction, I will have to multiply the top and the bottom by x plus 2. Again, if I do it on the top, I have to do it on the bottom as well, and vice versa. Okay, so now on this right-hand side, left-hand side remains exactly the same. on the right-hand side, I've got ax plus a plus bx plus 2b all over x plus 2 times x plus 1. So I can combine my fractions once I have a common denominator. Are there any questions on what I've done here? Not necessarily why I'm doing it or where it's going, but what I've done. Okay? Okay, so I now have, take a look at this last equation down here. On the left side and the right side, my denominators are exactly the same, which means that I can multiply both sides by x plus 2 times x plus 1, and that will clear out my denominators. Which leaves me with 2x plus 1 is equal to ax plus a plus bx plus 2b. And this equation has to hold for all values of x. So we're trying to find an a and a b that make this equation hold no matter what x value we have in there. We want all x values to work. So what that really means is that this number in front of the x on the left-hand side had better be the same as the number in front of the x on the right-hand side. So what I might do here is I might group my x's together. I've got an ax plus a bx. So if I factor out the x, I have a plus b times x. And then as far as constant terms, I have an a plus 2b. So I've regrouped and factored out so that I've grouped all my x terms together and all of my constants together. So I have 2x plus 1 is equal to this whole right-hand side. Now, again, in order for this equation to be true, the number in front of the x has to be exactly the same. And so my x coefficient on the left side is a 2, and that better be the same as my x coefficient on the right-hand side, which means that 2 has to be equal to a plus b. And my constant term on the left-hand side is a 1, and that 1, that constant term, better match up with my constant term on the right-hand side, which means that 1 had better be equal to a plus 2b. Okay.
Substitution and elimination now, right?
Yeah, so now take a look at what we have here. Our goal, again, is to find a and b, find values for a and b. We have 2 equations and 2 unknowns. So we've got to solve this system of linear equations, this system of equations here. Lots and lots of different methods for doing this. Again, go back to your college algebra file cabinet, and one way to solve this system is to take one equation and solve for one of the unknowns. So for example, I could take this first equation and solve for a. And a is equal to 2 minus b. And then I can substitute that into my second equation. So I have 1 is equal to a, which is 2 minus b, plus 2b. And so now I have an equation that is just in terms of b. And I can solve for b on the second equation. So we've got 1 is equal to 2 plus b when I combine my terms. I subtract 2 from both sides, and I end up with b is equal to negative 1. Once I have my b, once I know what b is, then I can say, okay, well, b is equal to negative 1, which means that a is equal to 2 minus negative 1. And so our a value is equal to 3. Okay, so our original expression up here, this proper fraction 2x plus 1 over x squared, or I'm sorry, x plus 2 times x plus 1 is going to be equal to, well, the a is going to be 3, and the b is going to be negative 1. And so we can conclude that 2x plus 1 over x plus 2 times x plus 1 is equal to a, which is 3, over x plus 2, plus b, which is negative 1, over x plus 1. All right. So let's, oh, that's sad. Okay, so let's talk about what we have here, okay? This is our proper fraction, which means that our original, the x cubed plus 3x squared plus 4x plus 1 over x squared plus 3x plus 2. Let's see, so good bookkeeping would say, okay, we have to go back. Remember, we had an improper fraction, and we had its whole part, that was the x, plus its proper part, and that was this part up here. So our final conclusion, once we put everything together, is that we have x plus 3 over x plus 2 minus 1 over x plus 1. And so this is our conclusion. That double asterisk that I put down in the original calculus where I said, oh yeah, we can just rewrite this fraction as this stuff, and then we can integrate that stuff. All that work went into the asterisk. The calculus part was easy. The algebra part takes some time. It's not hard, it just takes time. Okay, any questions or comments about that?